Hello everyone, I'm Saman Sayahlatifi, and I'm a PhD student in mechanical engineering at the University of Alberta. For this presentation, I want to talk about the three-dimensional microstructure-based finite element simulation of cool sprayed ceramic metal coatings. And this research is going to be one of the steps towards establishing a multi-scale physics-based predictive modeling for autonomous material design and repair, especially for the application of ceramic metal composite coatings in oil and gas industry. In this slide, I want to show you a summary of the experimental and numerical efforts that we basically take in our research group to analyze and investigate the behavior of metal matrix composite coatings. On the left, you can see the figure mapping out the time scale versus length scale. And to begin with, I want to show you the typical experimental efforts that we take to investigate the behavior of MMC coatings. Basically, we do nano and micro indentation to assess the effect of ceramic particles on the hardness behavior of on the hardness of the metal matrix composite coatings, and plastic deformation of matrix and particle fracture are the typical mechanisms that we basically observe. As a second class of experimental tests, applied tests stand out, and dry abrasive and high stress abrasion or slurry experiments can be named in this category. And lastly, thermomechanical fatigue performance, in which cyclic behavior and cyclic deformation of the material is investigated. After doing experiments, we need to analyze the fracture surface and the failure mechanisms happening during the experiments, and we use diagnostics such as SEM to probe the failure mechanisms happening during the experiments. Basically, we have recognized two different categories of gaps to be covered. The first one that normally happens in lower length scales and time scales are in association with opportunities in experimental mechanics and computational mechanics of failure mechanisms in extreme environments in which the material undergoes high strain rate loading and high temperature. And then the second category of opportunities is related to the application of specific predictive modeling for materials and process design, which is normally related to end users in industry. And we think that there are different areas of improvements in performance of MMC coatings, and the one that I want to talk about and is going to be the focus of my PhD program is micromechanical finite element modeling, or physics-based material level modeling that pushes the state-of-the-art in computational material design and scale bridging. And the result of this research is going to be fed into homogenization approaches by which we bridge the micro scale and macro scale behavior of the material. And finally, we want to use machine learning approaches such as artificial neural network to bridge the scales by making fast predictive surrogate models for autonomous coating design and repair. And the result of this research is going to be used to train the machine learning approaches to make these predictive models. And the physics-based micromechanical effect modeling in this study normally is comprised of three different steps. The first one is the characterization of microstructure to collect data on the microstructure, for example, particle size, particle shape, and particle distribution. Next, by having access to this microstructure characteristics, we generate models with the aid of Digimat software, and then the assembly of generated particles and aluminum matrix is important to ABAQUS solver to apply the load, and in this case we applied quasi-static compression on the representative volume element generated by the Digimat software. And there's a big piece of validation, both quantitatively and qualitatively, and we compare our numerical findings with experimental ones. On the left, you can see the quantitative comparison, in which the stress versus strain histories for different samples has been compared to the experiments. For example, for pure aluminum, for the 34 weight % alumina, and for the sample reinforced with 46 weight % alumina. Basically, the results are in a good agreement. And on the right, you can see the history of predicted damage mechanisms. For example, at the strain of 4%, you can see that void volume fraction is localized in the thin ligaments between the particles as the indicator of damage, and with a further increase in loading, the well-known 4 or 5 shear bands are going to take form, which is also previously reported by previous studies. But they use two-dimensional RVEs, and in this research we have used three-dimensional representative volume elements to make a more realistic simulation. And also the occurrence of debonding and particle cracking is predicted specifically at sharp corner particles, which shows that this computational framework can be used to tailor the microstructure to obtain a bit of performance. And also these are the failure mechanisms that we have experimentally observed, as you can see on the figure on the left. And to recap on this presentation, there are two concluding remarks. The first one is that the qualitative and quantitative comparisons confirm that the proposed macromechanical approach provides in situ understanding of deformation and failure mechanisms, which are not accessible through our experiments, and this can result in material optimization by tailoring the microstructure. And then the findings of the subscale macromechanical model will be fed into machine learning approaches to bridge scales for autonomous design and repair of metal matrix composite coatings, which are going to be used in extreme conditions. And these are the references. Thank you very much for your attention. Please let me know if you have any questions.